So hello everyone, welcome to join the Tensor Learning Team seminar. My name is Chao Li. I'm a research scientist at Riken and also the host today. Well, in this event, I'm very glad to introduce our guest today, Dr. Patrick Gills. My pronunciation right?
Perfect.
Yes. Okay. Dr. Gill is currently a postdoc researcher at the Zeus Institute Berlin, working in the Department for AI in Society, Science, and Technology, together with Sebastian Pokcha. He leads the research group on quantum computing and optimization, which is engaged in the development and application of quantum optimization algorithms and tensor-based methods. Dr. Gill studies mathematics and physics and defined a PhD in 2017 at the Free University of Berlin. And since then, he has been working on different projects on complex dynamical systems, transfer operator theory, and quantum information. The scientific research of Dr. Gills is focused on tensor decompositions, aiming at the development and application of novel concepts and techniques for various tasks involving high-dimensional state spaces. Well, the whole event today will last for about 1 hour. At the beginning, we will have a talk given by Dr. Gills for about 45 minutes. The title of the talk is the Tensor Train Format and its applications. And after that, we will have a Q&A section lasting for about 15 minutes. So if you have any questions or comments about the talk, you can send a message through the chat box of the Zoom during the talk, or in the Q&A section, you can just turn on your speaker and ask your question directly. So hope all of you can enjoy the event today. Let's welcome Dr. Gills to start his talk.
Yeah, thank you very much for the nice introduction. So yeah, the title of my talk is the Tensor Train Format and its applications. And I want to go through some different application areas. So like after clearing the basics of tensor decompositions, we will see some various applications of these tensor formats. So I always like to start with some motivation. And so since we are here talking about quite general aspects of tensor decompositions, the basic setting is in the end that we have a high-dimensional tensor, a high-order tensor T, which has n different dimensions. It can be complex, it can be real. And we want to work with this tensor. We want to do something with this. And like the problem is, which emerges directly, the curse of dimensionality. So the storage consumption of our tensor can be estimated by O of d to the power of n, which means that we have an exponential dependence on the order of our tensor. And so to mitigate this curse, we can actually use different tensor formats ansatzes. So one of the most basic is the canonical format or CP format, where we express our given tensor as a sum of rank 1 tensors. So here we already see that we do not have this exponential dependence anymore. But there are other drawbacks of this format. So another option would be the Tucker format, where we decompose our given tensor in some kind of core tensor with different attached smaller tensors or matrices in this case. Here we have a stable format, but we again have the exponential dependence on n. And so one of the most promising and potentially most usable formats is the tensor train, the TT format. So here we decompose our tensor into a chain-like network of smaller lower order tensors. And in this case, we see we do not have the exponential dependence on n, and we here actually have a stable format. So this is the one we want to look at in more detail in the following 40 minutes. So anyway, if we work with tensor formats, the one of the main aims is always to work with low-ranked tensors. So this ensures us then to really reduce the storage consumption and the computational costs at the same moment. Okay, so let's go through the basics. Maybe some of you know this already, but I will recapitulate it anyway. So what is a tensor? A tensor is a multidimensional generalization of the matrices or vectors. And order 1 tensor is a vector, and order 2 tensor is a matrix, and order 3 tensor is, you can imagine, as layers of different matrices. And we distinguish between 2 types, so to say. We consider tensors T in C to the capital D. So this is a notation for C to the power of D1 times D2 up to Dn. And we consider tensor operators L, which live in the space C to the D times D prime, for example, here. And just as in linear algebra, we consider here a linear space of tensors. This is C to the power of D, and the linear maps between 2 of these tensor spaces. And as you can see here already, we can simply generalize matrix multiplication, matrix addition, and get our basic calculation rules for these tensor formats, or for tensors in general. To then use tensor formats, we have to rely on the so-called tensor product. This is the basic foundation for all these tensor products. So if we have 2 tensors, T and U, with different modes, so one has D1 to Dn, the other one has D1 prime to Dm prime. And if we now compute the tensor product of these 2 tensors, we get a new tensor, which has order n plus m, and each entry is given by the corresponding product, or the product of the corresponding entries of T and U. And to give you 2 examples here, the first one is the tensor product of 2 vectors, which is also called the outer product. This then defines as a matrix, and the entry in the row I and column J is given by the i's entry of U and the j's entry of V. And if we multiply to a matrix and a vector in the tensor product, then we get order 3 tensor, as you saw before. And here, every layer is defined as the matrix M times the corresponding entry of V. Okay, so let's just consider a very small example, which already makes you see the potential maybe of tensor train and tensor decompositions in general. So we have an order 3 tensor where we know that the first layer and the last layer is actually the same, and we have a different one in the middle. And to decompose this order 3 tensor, the first step is that we take these layers and multiply, for example, the first layer with the vector 1, 0, 1, which means put it in the first layer, not in the second, and then in the third again. And we take the layer from the middle and multiply it in the tensor product with the vector 0, 1, 0. If we now decompose these 2 matrices even further, we get our canonical decomposition of this tensor. So we have now a sum of 3 rank 1 tensor products, which if we would contract these tensors here or these vectors and add them, we would exactly get back our initial tensor here. So what we mainly focus on is some notation like this. So this is a core notation of the tensor train format. And here in this case, you can understand this as the generalization of matrix multiplication. So just as multiplying 2 matrices, we here compute the tensor product of the corresponding entries, which are vectors in this case, and not only scalar values. And then we sum over the rows and columns respectively. And if we do this, we get back exactly our initial tensor again. So what we can see here in the end is that, I mean, if we disregard sparsity and just ignore that we here consider a toy example, for the representation in the canonical format, we need 27 entries. And for the representation in the tensor train format, we need, let me see, it was like 24 entries, I think. 9, 18, yeah, 24 entries. So even this little example, we see that using the tensor train format may enable us to reduce the storage consumption of these representations of finite dimensional tensors. So the very basic definition of the tensor train, or also called the matrix product state format. Just as like a side note, the tensor train format was introduced to the mathematical community around 2009, 2008. And then it quickly turned out that this format was already invented almost 20 years ago in the quantum community to represent quantum states, and that was called matrix product states. So what we do actually is we take a higher order tensor and then we decompose it into a set of smaller dimensional tensors of all the three tensors, the T1 to Tn, which are called TT cores. And for each of these cases here, we compute the corresponding vector. So this is denoted by the color here in the middle. And compute the tensor product of these n vectors for each choice of the case, sum over all possible combination of the rank indices case. And then we have our decomposition of our tensor T. So this is just like the very explicit definition of the tensor train format. You will see some other types of notation or one other type of notation in the following slides. Actually, no. So this is graphical notation. So if you want to work with high-dimensional tensors, this graphical notation can really facilitate the work, the expression, the construction, and the contraction of tensors. So we here have like a very simple notation. So we depict every tensor by a circle. And then we add n different arms, which indicate the three indices for an n-order tensor. So we have a vector, we have a matrix, order 3 tensor, order 4 tensor, and so on. And if we now want to combine, like multiply, contract different tensors, we simply join in this notation the corresponding arms. So if for example, if I multiply a matrix and a vector, I join the two arms here, the corresponding arms, contract the cores, and then I get a new vector. So matrix times vector as a vector. And you can also use this for tensors with higher order to construct like contractions of TT cores and so on, and to represent the entire decomposition of a tensor train or of a given tensor. So here on the left-hand side, you see a rank 1 product. So we have 4 different vectors in this case multiplied in the tensor product. Here we have a low order tensor train. And what you see here is a tensor train operator, or an MPO, matrix product operator. So in fact, actually, we can take any tensor we want, any order n tensor as complex as it can be. And in fact, we can decompose it into the TT format. So we can find the decomposition. And this works as follows. So this is just like a very rough overview of the procedure, higher order SVD. So we take an initial tensor, which has order n. The first step is we reshape this tensor into a matrix where we isolate the first mode, D1. And then we apply an SVD to this matrix. And what we then get is like an orthonormal part. This is the half-filled circle here on the left. And we get the part sigma times V transposed, which is then contracted to the residual tensor containing the other indices, or the other modes. And so now in the first step, we isolated the first mode. So we got our first TT core. And now we repeat this procedure. So we take the residual tensor, reshape it in a matrix again, or in this case, actually order 3 tensor to split up the second mode. Then we again apply an SVD and so on. And if we proceed until the right end of our tensor, then we get a left orthonormal, so I will get back to this concept in a few minutes, left orthonormal tensor train decomposition. But the point is, in the end, so we are not interested in going from full format to tensor trains. So we actually want to work directly in the TT format, and we do not want to leave it during our calculations, or not in the sense that we want to compute full representations of tensors. So just to show you like the basic calculation rules in this case, because we will need them here, before I go into the applications and so on and the different solvers. If I want to add two tensor trains, I can use the core notation like this, and then directly construct the sum of these two tensors T and U. In this case, the ranks of our tensor of the sum are the ranks of T plus the ranks of U. If I multiply a tensor with like some constant, then I can actually plug this into any of these tensors here. You can even like split up this constant and so on. So this is quite straightforward. And if I multiply two tensor trains, or tensor train operator and a standard tensor train, an MPO and MBS, I get a network like this. So I join the corresponding arms, the corresponding modes. In the case of the operator, these are the arms pointing upwards. So these are the column dimensions. And these are combined, contracted with the modes of our tensor train here in green. And if I now contract these cores here, then I get a new standard tensor train given here in orange. And here the ranks are actually given by the product, or they are bounded by the product of the ranks of the operator and the tensor train. So, but in practice, using SVDs, as you saw, like these a sequence of SVDs, there are many cases where we can then significantly reduce the ranks of our product. Okay, so another basic aspect, which you already saw in the slide where I decomposed like a high-dimensional tensor, is orthonormality. So if we have a core of a tensor train T, then we define two metrizations, unfoldings. This is the left unfolding and the right unfolding. And so this is actually just like take the core and combine the modes dimension with one of the rank indices, and then reshape it into like one of these skinny or fat tensors matrices. And what we then define is this core is called left orthonormal if we know that the product of L transposed or the conjugate transposed times L is the identity matrix, and if it's right orthonormal if the right unfolding multiplied with itself leads to the identity. So in pictures, and this is what you saw on the slide before, we use these half-filled circles, and the white part indicates which modes we have to contract to get the identity matrix. So this is there are practical aspects why we are very interested in this, which we will see during solving systems of linear equations or computing pseudo-inverses. And this is actually what I want to explain now. So assume we have an operator A and a right-hand side B, both in TT format, and we want to solve the system of linear equations AX times B. A times X is equal to B, and X should be in the TT format too. So there are different methods, different algorithms which can actually use to do this, and this is not a complete list here. So these are actually the basic ones. And what I want to focus on is the alternating linear scheme, the ALS, or also called DMRG in the physics community. And so this is one of the most basic algorithms, which is actually the foundation for the other two here, which you see on the slides, and for other algorithms as well. So what we do, so I will go through this step by step. So we have our operator and we assume that it's symmetric positive definite. This is actually, from a theoretical viewpoint, a very important property, but from practice we know that there are examples where we do not consider symmetric operators and can still apply this algorithm here. So it has some remarkable properties actually, but which cannot be proven. So okay, we say X prime solves our linear system here. This means that X prime minimizes the functional you see here, the functional J. You can derive similar expressions, similar terms for non-symmetric operators if you multiply it from the left-hand side by A transpose. But so for symmetric positive definite operators, we have exactly this functional here. Then we consider the retraction operators. So this actually PXI, this operator applied to a tensor core Y, actually takes all fixed cores. So we want to optimize one core after another. And so it takes all the fixed cores and then just plugs in the given argument, given tensor core Y into the correct position here. And so what we now do is we take our functional and we take our retraction operator and combine them, and we get a new functional acting on our tensor core which is to be optimized. And if we want to minimize this functional, we consider the gradient and want to find points or solutions y where the gradient is 0, which leads again to a system of linear equations, but a low-dimensional system of linear equations. So this is really only in the space of the dimensions of our tensor core. So not only the mode I, but also like the product with the rank R I minus 1 and R I. So in pictures, this looks like this. So we have an initial guess, and here we assume that it's already like in the correct form. So we have the first cores are left orthonormal, and the last cores are right orthonormal. And the core we want to optimize here in the middle, it's something else. So you cannot completely orthonormalize one of these tensor trains. So we consider our linear system, our system of linear equations, which we saw on the slide before. So this is the low-dimensional system. And then we actually construct the tensor network where we take the operator and multiply our initial guess from below or from the left and from the right. And we leave this gap here for the solution for our optimized tensor core. And we do a similar thing on the right-hand side. So we multiply B from the left with the retraction operator. So, and what we now actually just have to do, we have to solve this linear system here. So we take the upper part, this tensor network, matricize it, so reshape it into a form of a matrix, take the right-hand side, reshape it into a vector, and then we can solve this linear system. And what we get is the updated version of our tensor core Y in this case. And so then after some orthonormalization steps, applying SVD, we can proceed to the next core. So either going to the left or to the right, and can update the next core. So, okay, one of the last, let's say, theoretical aspects or methods which are important for the applications following on the next slides is the pseudo-inverse. So we know from standard linear algebra that the Moore-Penrose inverse is uniquely defined by these 4 properties. So we have a matrix A, which must not be square, and which has not to be square. And then we know that point 1 to point 4 define the Moore-Penrose inverse. And we want to adapt this, or we want to generalize this to tensor train decompositions. And what is important, why we want to do this, is there are some nice properties. So if we use the pseudo-inverse, so if we have a underdetermined or overdetermined system of linear equations, we can find a solution. So we have to move this window here. We can find a solution in form of A plus times B, and this is then a solution of the least squares problem. So actually, it's a solution which has the minimum L2 norm or Euclidean norm. And if we have an SVD of this matrix A, we can directly take these components here and construct our pseudo-inverse just by like flipping around the U and V matrices and inverting the singular matrix sigma in between. So this is actually a trick we want to use for tensor trains, and therefore we use the orthonormality of our tensor cores. So what we do here is we have an initial tensor train, which, for example, you can imagine it contains data. So the first modes, D1 to DL, are the state space dimensions of our samples. And the other modes encrypt the sample indices. So we have, so like theoretically, we can have like the tensor product representation also for our different snapshots. Or maybe we have a decomposition of it. So what we can then do is we left orthonormalize the green cores and right orthonormalize the blue cores. And we simply keep the last singular value matrix in between. And to then get the pseudo-inverse of this construct here, we simply flip around the components, and there are different ways of understanding this, but so one way is to see this here as a cyclic tensor train. So actually now we have the rank 1 in the middle of our network, and rank RL connects our last and first core. Okay, so this was like the theory, the methods, the concepts we need. And now let's go to the different applications which we considered in the last 10 years roughly. So at the very beginning, we started with chemical systems. So we say we have n chemical species in some environment, and these chemical species interact through m different reaction channels, R1 to Rm. And we know that the probability of a firing of one of these reactions is given by propensity A mu. And then we also defined the vector of net changes, so like the change in the number of molecules through this reaction R mu. And then we can write down this in form of a Markovian master equation. In this case, it's called the chemical master equation, which describes the probability distribution of our system being in different states at different times. And so this is quite standard, but what we can now do is we can take this and rewrite this in a tensor-based format. So actually we can use directly tensor train format for this and have then linear ODE in TT format for our probability distribution, which we can then solve by applying different time integration schemes like implicit Euler or Crank-Nicholson or something like this. And so what we then, for example, what we computed here in these cases is the mean concentrations of our molecules in our systems, or how close we are to the stationary distribution, to the stationary probability distribution. Or here again, we have mean concentration. So this was like the very first application of these tensor trains for me and for my colleagues. And then directly from this, we went to catalytic systems. So here we can actually do quite similar things. So the setting is a bit different. We have some we represent the surface of our catalytic catalyst as a rectangular lattice, and we have different sites, different types of sites. So here in this case, CAS and bridge sites, and on these sites, different molecules can be adsorbed. In this case, it's CO, oxygen, and the other state is the empty state. So we have 3 states per site. And we apply some periodic boundary conditions in our tensor, so which we can also include. And yeah, the aim is to take or to construct a Markovian master equation, in this case inspired by the chemical master equation, to model these rare event dynamics and to extract key quantities from these systems. And what we know is that in this case, for this multi-scale model, which you can see here, so it's ruthenium dioxide, we know that the kinetics mainly take place on the CAS sites, and the interaction between the bridge sites can be, to some extent, can be neglected. And this is what we do. So we take one ring of our torus here, and this can be then described, or the probability distribution on this segment can be described by a tensor train, or can be expressed by a tensor train. So we did several experiments. Here in this case, we changed the environment parameters, so like the CO pressure. We increased the number of sites. We increased the stiffness of our system. So what we saw in the end, so we can, like on one hand, we can extract these key quantities, and we get an almost perfect agreement with the kinetic Monte Carlo, with the simulation results in the end. There are settings which can be solved quite easily, so where we can solve tensor-based eigenvalue problems by the ALS, and this just takes a few seconds. But if we go to the peak here in the TUF, in the turnover frequency, which describes the efficiency, we see that the system gets more, or like the course gets more correlated. So the correlation length increases, and so the ranks increase of our tensor representation, and this makes it a bit more difficult, but we can still extract these important points here. Yeah, and yeah, for like increasing stiffness, we also see that the tensor train approach shows very small dependency actually on this. So to generalize this, the next step was to construct nearest neighbor interaction systems in general. So not only some catalytic processes or chemical reactions or whatever, but in general, some network where we only allow interactions between adjacent cells. And these cells can be quite various systems. So what we can do is we can write down a compact description, a compact representation using the core notation of the TT format. This is or this applies to actually to all cyclic or non-cyclic nearest neighbor interaction systems. And to show you a few examples, we considered in this paper, we considered the Ising model, we considered some oscillators, coupled oscillators, and some Toll station model. So, and all these models were described by some Markovian master equations, which actually can be, or the operators of these equations, these master equations can be automatically constructed by our methods. And yeah, one very important fact is if we have some homogeneous systems, so where we know that the operator has the same coupling between each core, so we have the same interactions between every pair, then we know that the size or the ranks do not depend on the size of our network. Okay, so the next topic, the next bigger field was dynamical systems. And here we were interested in adapting different data-driven methods to the tensor train format. So the first one was DMD, dynamic mode decomposition. So here we assume that we have different snapshots, T0 to Tm, for example, like temperature or velocity fields. And we assume that there's a linear relationship between these snapshots. So the snapshot tk1 times L, or L times tk minus 1, is equal or very close to tk. And we want to find the optimal tensor train operator L, which describes this relationship here. And what we use is the pseudo inverse. So we take our data matrix in this case. Then we, exactly what I described a few slides before, we left out and right orthonormalize the respective cores, and then we get our pseudo inverse. And by using this pseudo inverse, we can actually construct an explicit representation of L. And we applied this to actually various systems. So here you see two of them. There's the rotating annulus. So we have some water and some heated tank, and it's rotated. And then if you have the or match the correct frequencies and so on, then you get some patterns in your heat distribution. And so this data can be analyzed by tensor-based DMD, and we can extract these DMD modes, which describe some stable or in some sense coherent structures in our flows. But actually, it's not so. Don't quote me on this. So DMD modes interpreting is quite hard. Okay, so the next big algorithm was Cindy, so which was introduced a few years ago to for reconstructing dynamical systems. So we have data in form of X and Y. So we have like our data points and the derivatives. And we want to reconstruct the ODE behind these two data sets. So we assume that there's some dynamical system, and we want to reconstruct the governing equations of this. So what we do is we take some, or what Cindy does, here we take some basis functions, psi1 to psi p. We construct our transform data matrix here in this case. And then we can solve an optimization problem or minimization problem, and we get our coefficient matrix, which then multiplied with our basis functions tells us the reconstructed dynamics. So we can then write down the relationship in form of equations again. And if we take the right basis function, so this is something which can be discussed quite extensively, but if we choose the correct basis functions, we maybe really reconstruct the dynamics behind this data here. So what we then did with Mandy, so we go from Cindy to Mandy, we go from sparse identifications to multidimensional approximation. So here we take basis functions, but in this case, we define these basis functions in form of tensor products, of rank 1 products in this case. There are different types. So like specifically, we introduced the coordinate major and function major decomposition, where you go through your dimensions and keep the functions, or the other one would be you go through different functions and keep the dimensions in each core. And this enables us to represent a extremely large amount of basis functions in a very compact form here. And so what is important is we do not consider sparsity of our tensor cores, because this would make not so much sense, I would say. But we go to a different concept, to data sparsity. So we're not interested in results which have zeros everywhere, so as much as possible. But we want to consider data sparse representations. So we want to have low rank representations. And what we do is we take our basis here, our transformed data tensors, and then we can construct our transformed data tensor. And then again, we have a minimization problem which we have to solve, and this can also be done by using the pseudo-inverse. So, and here you see a few examples of actually quite high-dimensional systems which we computed and which we compared with like the classical approach. And so, if we have our data in the correct format and we have the correct basis function, or not correct, but suitable basis functions, we see that we can reconstruct the dynamics. We are very close to the actual solutions. For some cases, I can move this here, as you see in the right-hand picture on the right-hand side here. And we can reduce the CPU times and the storage consumption significantly. In the Kuromoto model, which you see here below, we took some data, we simulated the system, we took this data, reconstructed the dynamics using tensor trains, and then we choose a different starting point for our oscillators on the circle, and then we want to reconstruct the dynamics. And as you can see, so for quite some time we are able to estimate the position of our oscillators quite accurately. Okay, so then another application area is of course supervised learning. So these tensor decompositions enable us to take high-dimensional data and represent it in low-dimensional form. So this is so more or less obvious that it may be potentially applied to supervised learning problems and to benefit from this fact. So what our intention was, so we want to take Mandy, so which we introduced in the context of system identification, and apply to more general supervised learning tasks. So in this case, image classification. So we take the MNIST data set, which consists out of, I think, 40,000 or so handwritten digits, and also the MNIST data set, which has some pictures of clothes, but let's focus on the MNIST data set here. So we take this data set, and for each pixel, we define a different tensor core, and this is given by cosine and sine of alpha times the corresponding pixel value. So we are talking here about grayscale. This was some idea from colleagues from Saunmeier. And so now we here have our basis, like we here have our transformed data vector in form of a tensor train. And we can actually, either we can go straight forward and use the pseudo-inverse, what we can here do. So we can use the pseudo-inverse as you saw for Mandy, but we can also do like kernel-based Mandy, so where we apply the kernel trick. So in this case, we know that our coefficient tensor is given by y times our pseudo-inverse of our transformed data tensor. So this was like the setting for Mandy, or what we used for Mandy. But we can also rewrite this using the kernel trick. So rewriting or like finding or plugging in alternative expression for the pseudo-inverse. And what we then get is the Graham matrix. So we only have to take our transformed data tensor and multiply it with itself. And then we get a low-dimensional matrix, G, which then can be used to solve this minimization problem. So in the end, if you have some specific kernels, then you can write it as a product of local kernels. But so what we can do in the end is we take this part here, y times g plus, solve this system of linear equations, this low-dimensional system, and then by using that we get a decision function for our classification or regression, in this case, classification problem. So there's different opportunity or different possibility. So we can stay in the tensor train format without using a kernel trick, and we can adapt the ALS or DMRG. So this was some algorithm we introduced in the context of image classification, but which we actually use and plan to use for a lot of different applications, because it's very similar to ALS, but here we do not have to consider some square operators. We do not have to consider symmetric operators. We here assume that we have some tensor train representing our data with additional index given these encrypting these samples. And there are different ways of representing this, but we can for all these ways we can approach these minimization problems, these regression problems in the end by ARR, by alternating ridge regression. And so what we did for MNIST here in this case is we have 10 different digits, and we have one hot encoding. So we have like a right-hand side with like in dimension an r to the or n to the 10. So we have 0 ones and a vector with 10 entries. And for each of these rows, so for all snapshots, for all training snapshots, we solve ARR. We solve the minimization problem using ARR, and then we can construct our coefficient tensor simply by multiplying these respective coefficient tensors or coefficient tensor trains, multiplying it with like the respective unit vector, and summing over all these things. So now let's come to the results here. We took the MNIST data set. We considered like reduced images and full images just to get some more feasible set of data points which can be approached by metrics and by tensor-based methods. So what we can see is that we reached nearly, I think it was something like 97.8% classification rate, which is quite good. So there are some deep neural networks which get better results, but for the first try, we were very happy that this worked out. And we can see that the misclassified digits or images are sometimes very hard to recognize even for humans. So these results show that actually tensor trains and this concept of tensor product-based basis decompositions has some potential for image classification and for regression. So one of the current projects is we want to train neural networks by using tensor trains. So we consider a single layer neural network where we have some input layer, then we have some hidden layer containing our activation functions, which are actually kernel functions which depend on the parameter eta, and then we have our output layer. And this neural network can be seen as the weighted sum over our activation functions evaluations. And we take this expression actually, so this is the idea here, and use the law of large numbers and say, okay, for as n goes to infinity, this expression converges to the integral, which you can see here. And so what we do is we define the integral operator, and we take again some set of basis functions, and then we can derive some algebraic formulation, actually a Tikhonov regularization of our problem here. And we want to solve this to find the tensor lambda, which is a tensor train again, which gives us the coefficients for combining our basis functions for this problem here. So just to show what is the new idea here, more or less, is we take our basis functions as rank 1 tensors again, so which we also did for Mandy. And now we take our activation functions, and there are some standard activation functions which are actually quite simple, but they are hard to decompose in the tensor train format. But we found some suitable decompositions which are scalable, and we can then take these, construct a tensor network, and then we take some delta tensor, which then combines our mode indices again, or like the sample indices in this case, to ensure that we really consider the correct problem. And then we have some functional tensor trains here. So we're computing here the integral of the continuous modes over the continuous modes of our corresponding tensor cores. And the coefficient tensor is then again given as a tensor train. And to solve this problem, we use ARR again. And we could show that the local Tikhonov regularization we use in this case, so the parameter in front of our matrix, of our identity matrix, to regularize our system, the local Tikhonov regularization is actually equivalent, or it's the same as the global one. So we have the same prefactors for this. Okay, and one example we considered so far is the concrete compressive strength prediction. So we have here a data set of different properties of our concrete, so age, amount of cement, fly ash, and so on. And we want to use the Heaviside function, or our Heaviside approximation, and Chebyshev polynomials to predict from the data the strength parameter here in this case. And the first results look quite good. So we get quite good results compared to existing literature. Of course, there again, like neural networks, which give a bit better results, but this is not the important fact here. So this is more proof of concept for functional tensor trains and all this alternating ridge regression stuff. And I think I have to hurry. So what we can see is for different ranks of our solution, we see that the accuracy on our training sets gets better, but the accuracy of on our testing set is more or less the same. So which means that for this specific set of parameters here for our regularization, we already get like the optimal result on our test set, with respect to the used basis and the used activation function here. Okay, so let's go quickly through the most current topic, I would say, quantum simulation, quantum computation. So actually, we want to go back to the origin of MPS, MPO, and want to use the insights of the tensor train approaches from the last years, and want to see if there are some routes which we can take to maybe speed up quantum simulations or find frameworks for constructing quantum algorithms. So just to give you a brief overview, so we have here a quantum circuit, which is a sequence of quantum gates. And in the last years, there were many publications, so many applications of MPS or tensor train formats to the quantum states to reduce their storage consumption. But what we wanted to do is we wanted to apply tensor train operators, or we wanted to use tensor train operators to construct the quantum circuits itself. And the hope is to speed up these quantum simulations to reduce CPU time, and also to use this framework for constructing machine learning or optimization algorithms on quantum computers. Okay, so the basic ingredients are here: the decomposition of single qubit gates, which act on n-qubit systems. So we have potentially large quantum registers, but only at one position we apply some specific unitary operation. We also take into account controlled gates. So here we have rank 2 tensor train decomposition for any controlled gate, acting on two qubits in our systems, which do not have to be adjacent. And then the double controlled gates, where we again get a rank 2 tensor train decomposition and have different operations at our target and controlled qubits. Okay, then one very important aspect why we actually are interested in combining MPS, MPO, TTT, and quantum circuits. There's a generative sampling technique, which which I think is well known in the community of tensor-based quantum physicists, which is not so large. But so this is quite simple. So what we can do is we can take our wave function. We construct a tensor network here, so I do not go into details. But so if we consider higher order, high dimensional quantum systems, we cannot construct these probability distributions at once. So we have to sample actually the same Qiskit does, so for example. But here we take this network, we contract the course we are interested in, or we are not interested in, with some vectors of all ones, and then we can go through this tensor network step by step and sample outcomes of our measurements, which then correspond to the probability distribution which is given by our wave function here. This is a very efficient method actually to generate a lot of samples. And one application example we considered in the paper was the quantum full adder network. So this is the quantum full adder is one of the first basic circuits introduced into quantum community, quantum computing. And this actually just adds 2 qubits A and B and a carry in qubit C in, and produces a sum S and a carry out qubit C out for the next significant digit. And we can write down a compact expression of our quantum gate here, or quantum circuit. So this is a single quantum full adder. And we see we have rank 4, which is in this case, so like the maximum possible rank of a network in this size of a tensor train operator would be, let me think, in this case, it would be 16. No, we have here 2 times 2, 2 times 2. That would be 16, yeah. So we have, so to say, a low rank decomposition. And what we then, so to construct our quantum full adder network, we simply take this G here above. And so like we take different quantum full adders and just combine the last and the first cause of all decompositions. And so we get a rank 4 decomposition of arbitrarily large quantum full adder networks. And we can directly simulate it using our tensor train or tensor-based methods. So we computed 1 million samples for different numbers of QFAs in our network. We saw that we get the same results as Qiskit, so which we expected actually, but because this is like an equivalent approach. But what we also saw is that our CPU time is much lower than this time Qiskit needs, or even this time what Qiskit needs if we use an integrated MPS simulator. So we only have a linear dependence, a small linear dependence on the number of QFAs, and we have an exponential dependence in the case of Qiskit. And for example, if we consider 100 QFAs, which is something like, I don't know, like nearly 400 qubits, then I think we only need 30 seconds to compute the probability distribution, or to sample the probability distribution. Okay, so as last slide, I just want to mention that all the methods we used, all the examples, nearly all the examples we considered in the last years are included in our toolbox scikit-TT, which is open source. So it's a Python toolbox using basically NumPy and SciPy. We have a tensor train class, which is quite powerful with lots of different attributes and subroutines. And we have model building. We have different solvers for systems of linear equation, eigenvalue problems, ODEs, and yeah, we want to find as many as possible application areas for our toolbox. And now quantum simulation is the newest one in this case here. Okay, so that's it from my side. Thank you for your attention.
Yes, and thank you very much for the impressive talk. There has lots of questions in the chat box.
Okay.
The first question is from Cisa. The question is, in your applications, is there any theoretical TT rank, or you need to turn the TD ranks to data?
What I didn't understand the first part. Let me see. Can I see the chat?
Yes, in your applications, right?
Yeah.
Is there any theoretical TD rank, or you need to turn the TD ranks to data? You can find a question from the chat box of Zoom.
Yeah. It depends. So like the hope in the end is actually, so if we take for example one of these catalytic systems. So when we start considering like a low dimensional example where we only consider the low number of sites, then we do our calculations, or we increase the rank of our solution of our initial guess until we get like a accurate solution, I would say. So until we see that the error is low enough, then we can increase the number of sites, and the hope is that we get to some point where the rank does not depend on the system size anymore. So in general, it can be the case. In general, of course, if you have data which scales badly in some sense, that your rank will increase if your system size increases or if you increase the number of snapshots. So this can be the case, of course. Yeah.
So how about the answer?
What?
Okay. No.
Okay.
Okay. Let's move on to the next question. Is your TD approach to identification of the dynamical system able to work on chaotic systems?
Let me think. The truer circuit we considered, I'm not sure if it's really chaotic. So in general, I think the won't make too much sense. So if you have data and the problem of chaotic systems is if you just like include some very small error, you get completely different dynamic or trajectories in this case. So it's not really chaotic, but actually I'm not sure right now. Yeah, actually, yes. So like Schur circuit shows chaotic behavior. So we get there's small difference. So like we have our trajectory from a chaotic system maybe. So we have some starting point, and then we have the trajectory, which is like the result of applying these chaotic dynamics. And then we reconstruct these equations and we get something which describes our dynamics of our trajectory, which we have seen in the data. But so this is not that we then get some stable representation or something. So can still be the case that we can reconstruct the trajectories of what we have seen. But if we then just like tune the parameter or the initial state, and for example, truer circuit would produce some completely different outputs, it's not like guaranteed that we can like see this chaotic behavior in the same quality and quantity.
Thank you. The next question is from Andon. He asked that the tensor networks work well for quantum computing under the assumption that underlying entanglement structure allows for the low-rank decompositions. Is the low-rank assumption too strict? Is there a need to relax it for broader applications? Are there any attempts in this direction?
Mm-hmm. So too strict, so like the low rank assumption. So in the end, if you let's take quantum simulation. So if you want to represent these quantum states, these entanglements, so there's some practical limit in the end. So like you need low-rank decompositions to simply store the tensors, the quantum states or the probability distributions you consider. And so I wouldn't say it's too strict. It's not even like a real assumption. So I mean, like for simulating stuff and for finding coefficient tensors and so on, of course, we are interested in low rank approximations, but if we see, okay, we have to increase our ranks, we increase our ranks. So as long as we find a solution, maybe it's not so important to really find low rank, or like, in other words, what means low rank. So if we have like a high dimension tensor, and my solution, I don't know, like I get ranks of 100, which is actually quite large, and depending on the state spaces and on the mode sizes, this is maybe also too large to store the tensor. But so if I get something like this, I have a representation of a tensor which is maybe of order 100 and would require ranks which are extremely significantly higher than this. So yeah, I wouldn't talk about the assumption. It's a necessity. So we really need like low rank tensors to low rank representations to work with it. And other things, I don't know. Like there are different formats which are based on some slightly different contraction schemes. But so at some points you have to like restrict yourself to finite number of something, finite number of ranks of basis functions of whatever.
Yeah, thank you. The next question is from Mingyuan. She asked, for the Mandy and its related following methods, are the basis functions manually chosen? If they are, is there any way to decide them? Thanks a lot.
That's a good question. So that's like the same as for Cindy. So to choose the correct basis functions is actually not so easy. It's not clear a priori what are like the optimal basis functions. So this is like in practice, I would say. So I think there are some approaches which like decide for some basis functions, or maybe take a large set and then reduce it to some important ones. But in the end, find optimal basis functions is maybe sometimes based on try and error. So you take a set, you try to reconstruct your dynamics, and then you add basis functions step by step, and then you see what happens. So for the Mandy approach, we have like sets of basis functions for each dimension. So we usually take some, I don't know, monomials or piecewise constant functions or something like this, which gives us or Chebyshev polynomials, which gives us a part of a basis of our L2 space.
Yes, thank you very much. There's someone who have questions. Chibin, do you have a question?
Yes, I have some questions related to quantum computing applications.
Yeah,
no, I'm not familiar with quantum computing, but as far as I know, that you present that we can use TT representation to represent the quantum gate, like quantum operators. But in quantum computing, I think most of quantum gate are some kind of unitary operator, like CNOT or single qubit. So when we apply tensor train, are there any difference between standard quantum gate and the tensor train representation? I mean, some kind of expressive ability is similar or some difference?
There's actually a big difference, yeah. So I mean, so when we apply these tensor train operators to quantum gates or quantum circuits, we actually use unitary quantum or unitary MPOs, unitary tensor train operators. But like in general, so like what we did at the beginning, like the catalytic processes and so on. So this is quite close to some quantum systems. So I mean, we have different mode sizes and so on, but there is like from the basic structure, from this viewpoint, there are many similarities, but, and this is the point, let's call it expressivity. So if I do classical TT simulation, or like if I use tensor trains on my computer using toolbox scikit-TT for like the ODE and so on, we in general don't use unitary operations, or we do not restrict to unitary operations. So yeah, this is right. This is a restriction for like quantum computing in general. You only consider unitary operations, and so we have to do this in the end too. Yeah, so we take unitary tensor train operators in this case.
Okay, so if we use TT representation, I wonder if such program can be still running on the quantum computer, because this is not standard quantum gate.
That's a good question. So yeah, I mean, there are some things we are working on currently, and so we want to use the framework. There are also like quantum computing theorems or statements which tell you how you can implement non-unitary operations on a quantum computer. So there are then some tricks where we will use an SVD and split up the singular values and so on. So there are ways and methods, but I would say it's still not really clear how to translate from the one world into the other. So we have a framework which is very similar, which can be applied directly, but we have some restrictions which we have to deal with now, which we didn't have before. So this is still a field with a lot of open questions.
Okay, maybe a last question.
Yeah.
So, what we expect advantage? What kind of advantage we expect to obtain by using tensor chain instead of standard?
For quantum computation now, specifically, or you mean particular for quantum computation or in general?
Quantum computing in your last part.
Yeah. So like let's say the first advantage we aim at is to reduce the CPU times for quantum simulation. So we have different examples, for example, quantum Fourier transforms and so on. So if we can express parts or the entire circuits, parts of our circuit or the entire circuit as some low-rank tensor operator, we maybe, so it always depends on the example, I would say, but we can reduce we can speed up the simulation time for these systems. So this is more or less a practical use for simulating quantum circuits to like understand how they work. But what actually like the very first intention was to give a new framework. So there's tensor trains are not new to quantum computing, but the concept of decomposing these quantum circuits into or parts of it into low-rank tensor decomposition is actually not explored enough, I would say. So there are still possibilities. So I think, when we take, for example, so this is not clear now, but these are some ideas. So if we take, for example, the operator from our catalytic simulations, maybe we can take these tensor decompositions. So we have some structure TT slim decomposition there, and maybe we can take these parts and somehow derive some unitary operations from these existing decompositions, which then can be implemented more or less directly on a quantum computer.
Okay, thanks a lot. It's a great talk.
Thank you.
Yeah, anyone else who have questions or comments about this topic? If there's no one, it's the time to end the event today. Well, let's thanks again, Dr. Gills, for the very impressive, very remarkable talk, and also thank all of you for joining the event. Okay, hope to see you in the next Tensor Learning Team seminar. Okay, bye-bye.
Thank you very much.